Hello and welcome to this low-level JavaScript video where today, and in this whole series in fact, we are attempting to build the world's first RISC-V CPU on an FPGA using the TypeScript programming language. It's actually been a little while since I made the last one of these videos. A lot of people ask me if the project is dead or if it's coming back, and well, of course it is. You're watching it now, so it's back. In my mind, it was never gone. I just wanted to do some projects in between. I had some other things going on in my life that were taking time. So for me, it was kind of just on hold for a while. But here we are. And if you're watching this in a playlist in the future or something, and like you didn't notice any gap, or lucky you. Anyway, today we're looking at machine mode and privileged CSRs. Now, if you watched the previous episodes, and honestly, if you didn't watch previous episodes, it probably won't make tons and tons of sense. I mean, you can stay along for the ride in any case, get a feeling for it, and then if it seems like something that's interesting to you, you can always go back and watch them. But especially in the last episode, we started building out the CSRs, the control and status registers. Now, I will do a little brief recap of where we're up to, what we're doing, how we're doing it in general. But the CSRs in particular are a feature that's specific to RISC-V, so they're basically an address space that is separate from like regular memory address, program, ROM, RAM, whatever address space. It's an entirely separate address space that is 12 bits wide, and its purpose is to basically expose control registers for the CPU. It's just like a way of not having to sacrifice regular address space, and also there are some more details about atomicity and how you actually interact with these things. But in general, they're basically a set of registers that allow you to control the processor or its peripherals in some way. So in the last one, we looked at a couple of CSRs. We had a couple of CSRs that keep track of time. So RISC-V tells us we need to expose some method of keeping track of time. The way we do it on this system is just by exposing clock ticks. So there's however many clock ticks per second, and we expose a register where you can read that number out. It's 64 bits. So there are basically two. You would need to read it in two pieces, but there are kind of safe ways of reading that out so that you don't run into the edge conditions. But essentially, you have a 64-bit timer that tells you the number of ticks that have happened in the clock. And if you know the clock frequency, which in our case, it will be set at some frequency. I don't know what that frequency is yet because we haven't actually started with the actual FPGA yet. And the FPGA and all of the way that the timing comes together there is actually going to dictate a lot about how fast we can go. So the frequency is not completely decided yet. But anyway, that is a particular CSR. We also have the number of instructions that have executed and we have some timers and we have instructions retired. Now, machine mode is something that we've touched on briefly, but basically RISC-V has different privilege levels. So it's split up into, so far we've spoken about user mode. And user mode is all of the regular instructions and just the general functionality. And then when you have machine mode, it's sort of like this next it's actually the highest privilege level of the machine. And if you were to compare this with something like x86, it's like having a mode where you have full access to everything in the CPU and you can touch any region of memory you like and all of those kind of things. The kernel lives in that, so if you're using Linux or Windows or something, the kernel of the operating system is running in that. And then there's also then user space, and that's where all your software and everything runs. And if you want to do something that requires privilege, you have to go via a system call to the kernel, and you have to move into move into the privilege space via a system call, and the kernel will take care of that for you. In this processor, I don't plan on having any virtual memory or any kind of operating system-y kind of features, at least not in the beginning. And so this distinction is not a big thing for us, but there are things that we have to implement on machine mode in order to be kind of compliant. I think if you did see the previous episode, you'll know that I ran into some confusion about what is required for a RISC-V implementation to truly be a RISC-V implementation, and I still don't really have answers on about exactly what has to be implemented with machine mode. But for now, basically what I'm going to do is implement the machine mode registers that make sense, and we're going to use that as the basis for some continued things that we'll get into. So before we dive into all of that and I go into the summary of what we've done, let's just look at what we're going to look at today. So the goals for today are to understand machine mode, the CSRs, and how they relate to traps. Traps are like exceptions or interrupts. They're basically stuff that can happen in the processor, and then your code is going to kind of switch context and go and do something else for a bit. So in the case of a microcontroller, if you're used to microcontrollers, and this is basically what our RISC-V processor will be, it'll be like a microcontroller. On microcontrollers, you have interrupts. So for example, you might have an external interrupt that's like a wire connected to your processor, and when that changes voltage level from low to high, that triggers an interrupt within the processor, and it kind of saves the state of what it's doing right now, and it goes and runs a piece of code that either you or some library or the operating system or whatever you're using in that context has written, and it runs that routine, and then it will return, maybe not return to your code afterwards. So that's an external interrupt, but you can also have internal interrupts, right? If you set a timer and you want something to happen every time the timer kind of reaches its timeout, I guess, then you can also have an interrupt for that. And interrupts are actually the mechanism in a lot of operating systems for speaking to the kernel. So a user space program will trigger a software interrupt, which will cause control to move into the kernel, and then the kernel will say, oh, what interrupt was that? Oh, it was the user asking me to open a file interrupt. I'm going to go and do that stuff. So we're going to be looking at how that whole system comes together. We're going to be understanding what kind of code we need to write in the system, and I'm talking about kind of C code here, or assembly code. What kind of code we need to write there in order to set everything up, the whole environment. So, these things won't come for free. We're going to have to kind of put those pieces of code that handle certain situations, we're going to have to put them in our program. And in some cases, even if we're not using them, we're still going to need to set that stuff up. So that if those things occur, and especially if the exceptions occur, the code has something to do in those circumstances. And if the time allows, and I'm always a bit too ambitious with this stuff, but if the time allows for it, we're going to at least start with our first kind of exception, our first trap handler, and that's going to be when we try to access unaligned memory. So those are the goals for today. I've got some follow-up business that I want to go into, but first let's just do the very briefest of recaps of what's going on, because it's been a while for me, and I had to kind of get myself back into the project. It's probably been a while for you, unless you're watching this in the future. And so we're building a RISC-V processor, and in order to streamline that process, we're first building an extremely low-level emulator. And when I say low-level, I mean we're going all the way down to modeling the pipeline, and we're modeling all of the signals inside the processor as the signals that they would be, using only low-level bitwise kind of operations that we will have in the FPGA. And what this is doing is letting us do all the hard work of figuring out the design in software, where we have tons and tons of debugging tools that will let us know that our design is basically working as intended. Because when we come to put this on the FPGA, when we come to start working with the FPGA, we're going to bump into a whole bunch of problems that are going to be just difficult to resolve. They're going to be hard debugging problems, and they're probably going to be separate from our design. They could be separate from our design. You know, it's good to know at that point that we have a clear division between bugs in the system and just the myriad of ways that we can mess up in the FPGA. So it's just a kind of a way of making this easier over time. And I think it's really paying off, because I really expect that all of the kind of logic that we write here, we're going to be able to mostly duplicate in the FPGA, and all of the testing code that we write, like basically the C code that we compile and run on our emulator, those test cases, they're not test cases as of now, but they will eventually become test cases. We can try and run those against the real hardware as well and make sure that, oh, actually it behaves the way the emulator does. And if it doesn't, we've got something that we can investigate. So that's another reason that I think it's a really good idea. It gives us like kind of a sanity point, just something we know works correctly. So that's where we are so far. And we've built out the pipeline. This is a pipelined design, so multiple instructions are kind of running in parallel each clock cycle. And an instruction will take several clock cycles to complete, but we can actually run a bunch of them in parallel. Now, right now, this is another part of the whole philosophy here, is doing the most minimal example of the thing in order to make life easy, and then we're going to make it kind of more advanced over time. Right now we have a pipeline, but we're not running instructions in parallel. And that's actually a good way of doing it. I mean, there's things we need to consider when we actually do run instructions in parallel, but this will allow us to get the design down, even of the parallel architecture, before we actually do the hard part of running stuff in parallel. So it's just another way of breaking the problem down into smaller pieces so that we can attack them one by one, instead of kind of just having an overwhelming mountain of stuff to tackle. So we've got this pipeline design. We've got all the pipeline stages down. The pipeline stages are instruction fetch, where we go and grab an instruction from memory. We have instruction decode, where we kind of take the bits that make up an instruction and figure out, like, what are we supposed to do here? You know, we've got a bunch of ones and zeros. What do they mean in this case? The next step is execution. So in execution, we do all the math related stuff. So if we had an add instruction, that's when we're going to physically add the numbers together. The next, I might be, no, I'm not mixing my stages up, I think. The next stage is memory access. I need to double check this. It really has been a while since I worked on this. Memory access. Memory access is the moment that we go and access memory. So if our instruction was like, hey, go and load XYZ address, take whatever's in XYZ and put it in register 1, that's the moment we're going to do that. And then we have a final stage called write back. And write back is the moment that we take our result of whatever we've done in this instruction, be it add some numbers together or do some logic or read a number from memory, and we put it into a register. So we write it back to the system in that case. And we don't always need to do that, but some instructions will need it. So not every pipeline stage is active in every instruction, but every instruction does pass through every stage, if that makes sense. All right. So, what have I done since last time? I did a few things. one of the things I spoke about was adding this instruction, add upper immediate to program counter. We talked about that instruction a lot. We implemented a very similar instruction called load upper immediate, and we'd also implemented add. So this instruction, I just hadn't found a good moment to implement it. And I just did it kind of behind the scenes. And I talked about the fact that I might do that. And I can actually quickly show you. So if I run git show on this commit, add upper immediate to program counter, you can see not too much really changed in this. So now we're looking at the decode stage of the pipeline. You can see I added add upper immediate to program counter. That's just, was it this instruction type? Here we figure out if it was. We add a condition here. So when we're figuring out like which immediate we're going to put into, the immediate slot, basically we can reuse the logic from is load upper immediate. It's the same immediate, it's the same pattern, so we just add it here. If it was load upper immediate or if it was add upper immediate. I notice here I've used bitwise OR, and it doesn't matter because we use 0 and 1 instead of true or false in these cases. So this will equate to the same thing, but probably, either I should use just logical or just bitwise, but I shouldn't mix them, but I did mix them. And then in the execute stage, we got the same thing again. We just need to know, was it an add upper immediate? We need to pass a lot of this information down the pipeline. And here what we do is we figure out where we're going to branch to. So all I had to do was add in, again, this one more kind of OR condition. And then we end up figuring out the branch base. We did all of this before, so this was a while ago, but go and watch the old episodes to make sure this makes sense. It won't matter that much for now. And then here we pass along the branch address into the memory access. And we end up just passing these values down. We add one more condition here. And the write back value goes in here to the branch address. And this ends up being it. Yeah, because where is the addition taking place? I think the addition is taking place just by the sheer fact that in the decode stage we did this and we put the immediate value in, and now that immediate value already just moves into the execute stage where it does an addition, and it doesn't matter where it came from, right? It just does the addition. And yeah, so I did test this out. I think it works. I'm now doubting it. It's been a long time since I wrote that piece of code. So when did I write that piece of code? Back in November. So it's been a while. We'll check that. We'll make sure it makes sense at some moment. But that's one of the things I did. So this was just a small change. I actually limited 64-bit registers to 64-bit values. I realized I wasn't doing that, basically masking off the 64-bit maximum. So now I'm doing that. And now I'm also passing the program counter and also the program counter +4, I think, through every stage. So before it was only moving through the first couple of stages. I'm now moving it through every stage. And the reason I'm doing that, and we might need to do this with some more registers, we'll see, is that we actually want to track when an instruction caused a fault. And what I mean by that is, like, for instance, if we try to access a piece of unaligned memory, and by unaligned I mean like we can only access memory which is on sort of multiples of 4. So, well, not quite multiples of 4, but Yeah, it is multiples of 4. So if the instruction ends in 0, 4, 8, or 12, then it's kind of an accessible instruction if it's a multiple 4. If it's not a multiple 4, it means it's unaligned. And that means that we would need to access kind of 2 regions of memory in order to pull that data out. And what will happen in that case is that we're going to cause an exception to happen. You don't have to do this, but you can do it. You can also handle it in hardware, but I think this is a good one to start with. So what I'm going to do is I'm going to excuse me. What I'm going to do is to catch when we do that, cause an exception to happen, and then we'll write a piece of code that will actually kind of do the 2 memory accesses and return the value. So that's going to be our kind of testing exception. Yes, so that's why I did that. And also what I've done in the meantime is I've worked on some C code behind the scenes to set up the system. I've basically been improving the whole C code setup. So I've kind of improved the build system with a lot of help of a friend of the channel, Nate. He helped me bump up against some of the makefile nonsense that I encountered. But basically now we've got a bit more of a sane structure in here. And you can see here is just a basic program that we've been playing around with. And we also have the bootloader, which we talked about before. And now the bootloader also talks to some C code. So there's some C code here that's part of the boot up process before the main program runs. So before we even get to this code, there's a whole bunch of additional code here running. And there'll have to be more of that as well in the future, but we're not quite at that point yet. I'll talk a bit more about this in a minute. For now, we don't need to worry too much about it. But basically, we can now actually initialize global variables. So before, if we had a program like this, where we had an unsigned 32-bit number, and we assigned before the program even began, we assigned it the value 42. The way that it worked before was that if we loaded this program into memory, this 42 value would just be nowhere. It would be lost because nothing was actually making sure that these values that we define at compile time are actually getting into the right memory addresses in RAM, because we only have a program ROM, like we have a ROM, and we need to load that in. So I'll show you how that works as well. It's actually not anywhere near as hard as it sounds if you haven't done that kind of stuff before. And also, worked on the linker script. So the linker script is involved in this whole thing, boot files and assembly in C. And I've kind of sketched up the vector table. So, when we get an exception, the CPU needs to know where to basically send us. And the way that we define for the CPU where it needs to send us is that we place a data structure in memory somewhere called the vector table. And the vector table is just a series of addresses, basically. And you can think of it being like the first entry takes you to exception number 1, the second entry takes you to exception number 2, and so on. There are a fixed number of them, and when those things occur, the CPU just goes, here's the address where the table starts, add on the offset, jump to this address. There should be a piece of code that handles that. And that's why we need to figure out, that making sure that there's a piece of code that can at the very least, jump in there and return even if we're not using it. So, let's actually, now after quite some time in kind of the introduction here, let's actually look at M mode and the CSRs in the code that I've kind of pre-written here. I've done a bit of coding behind the scenes, not too much, enough to get us going today. And we'll kind of take a look at the spec as well, and we'll see what it has to say, and I'll do some kind of translation there, but at the very least you know where you can go and look to get some more information about the whole thing. So, in the CSR file, you'll see I've added an enum here called CSR mode, M mode, CSR M mode. M mode means machine mode, I'm not sure if I mentioned that. And what we have here is a whole bunch of addresses. These are addresses in the CSR space. Excuse me, it's really a bit dusty in this room or something. And they all begin with M, all of these ones. And M is for machine mode, so basically you can disregard the M when you're reading all of these, and so this is like the machine mode ISA register. This is the vendor ID, architecture ID, implementation ID. We have the heart ID, the status, the tvec, so that's the trap vector table, the interrupt enabled, interrupts pending, the cause, so that's to do with why something happened, the EPC, the scratch, and the tval. So I've actually explained all of these registers in comments down below. And yes, so we'll do some conversions here and everything. Like you'll see that here we have 64-bit registers for these other CSRs that we made. And in these cases, I've just made these numbers for now. And the idea is actually most of these will be constants. You can't even write to them. So I'm just setting them here as values. But I might change them to be register 32s or 64s, depending on if we need that. So the ISA, this encodes the CPU's capabilities. So the top 2 bits encode the actual kind of width of the machine. So like if it's a 32-bit machine, or if it's a 64 or even 128, that's encoded in the first 2 bits. And then the bottom 26 bits encode all the possible extensions that are present in RISC-V. And there are a lot of extensions. So let's actually go and take a look in the spec to see what it has to say about this. So this is the spec. And so there are 2 spec documents, as you know. Or as you may have seen in previous episodes. There is the unprivileged specification. Let's see what it's actually called. The RISC-V Instruction Set Manual, Volume 1, User Level ISA. And then there is this second document, which is the RISC-V Instruction Set Manual, Volume 2, Privileged Architecture. And this is what I mean by, the second spec document. So we worked for the most part out of this document while implementing the basis, all the instructions and everything. We still have some instructions to go, but and here this is the privileged stuff. So if we get to the machine level ISA, we'll see that there are a whole bunch of machine level CSRs that we need, and we have this one, MISO. So all of these things like WARL, they all have a meaning within the specification documents. It's a little bit hard to find it because sometimes things are defined in one document or the other, and they don't really, they don't always make it super clear. So sometimes it's tricky to figure that stuff out. But here we get the extensions, and so here you can see those first 2 bits. If it's a 1, then it's 32. If it's a 2, then it's 64, and if it's a 3, as in, and this means like if we have 0, 1, or 1, 0, or 1, 1, These are what these refer to in these cases, in those top 2 bits. Now the extensions, it talks about the standard extensions. So I'm trying to, so this tells you which bit we're talking about, and then from that bit, like, you can tell that we've implemented a certain instruction, so a certain extension. So here what you'll see is this number in binary. Let's have a look at it in binary, just because that makes things easier now. So okay, so we want to get this as a binary number, and we want to pad the start out to 32 with zeros. Okay, so you can see that we have 0, 1, which means we're on 32 bits. And we only have a 1 here, so which number is that? That's bit... that is the 9th bit. So if we look in the spec again, if it's the 9th bit, that means it's here. So that means we're implementing the base ISA, RV32I. We actually don't have any of the extensions right now. We may implement some we may implement some extensions in the future. Notably, we may implement floating point, because that's just a really useful one to have. We may implement the compressed extension, which is like smaller instruction sizes, which is better for packing instructions in if you're working with constrained memory resources. Integer multiply divide. There are a lot of things that we might want to look at there, but for now we just have the basis. So that's what this value means, and any program can read this, maybe as one of the first things it does, and figure out, can I do anything here? Though, if you're reading this to figure out if you can run 64-bit code, it's probably already going to be a bit tricky, but that's how it is. You can figure out what's going on from here. So next up, we have the vendor ID. If you've watched some of the live streams that I've been doing recently, and for those of you in the future, you can go and look at these in a playlist. They're the Bus Pirate, hardware hacking, the Bus Pirate streams that I was doing a while back. We encountered this JEDC. It's an organization. They basically keep track of vendors and products and standardization between like standard parts that people make, so flash chips and CPUs and all different kinds of things like that. And if you have one of those, you can put it here. And if you don't have one, you can put 0. I don't have one of those. I don't have the couple $1,000 or however much it is to register one, and I'm certainly not going to do that. So that's possible. Here we have microarchitecture ID. So here I actually want to take a little look at the spec to see what it says, but I have the feeling you can use this kind of to sort of version your own design. So it's a read-only register encoding the base microarchitecture. This must be readable, but a value of 0 can be returned to indicate it's not implemented. So a combination of vendor ID and architecture ID should identify the type of heart microarchitecture that's implemented. So in our case, we could use this field as we make revisions to the design. We can use this to basically say, this one's going to behave differently to this one. But 0 is fine for now. Processor version, same thing, right? It's the implementation ID. I'm really sorry about the coughing. It's really dry air in here or something. Implementation ID. Is there a specific note about that one? Let's have a look. Unique encoding of the processor implementation. It should reflect the design of the RISC-V processor itself and not any surrounding system. So I guess if you had peripherals, which we will have, for instance, we will have UART so that we can talk to other devices. That's not actually part of the processor. That's a dedicated piece of hardware in the FPGA that will perform that task, and we kind of link it together with the processor so that we can, speak to memory mapped I/O, or we can talk to CSRs that will control that kind of seamless interaction with that peripheral. But it's not actually part of the design. So in this case, if we change that, we wouldn't increment the microarchitecture ID, but we could implement the implementation ID, or rather the other way around. Well, I'm not entirely sure the way in which that should be done, but in any case, apparently this one relates directly to the RISC-V processor and not the surrounding architecture. Okay, so then we have the heart ID. I've talked about this before. Hearts are kind of like, well, they stand for hardware threads. You could kind of think of them as being cores. We're going to have a single core. We're going to have a single heart, so it's kind of not that much use to us. And it will have an ID of 0. And there should be an ID of 0 on the processor, so we kind of meet that just by doing that. Then we have M-status. So M-status holds a bunch of flags. Some of those are writable, some of those are readable. So it has like a global interrupt enable. So like you probably saw that I mentioned interrupt enable down here. So interrupts, there are a bunch of different interrupts that you might have, and you can enable them and disable the individual interrupts. But this one, in the settings, for instance, will allow you to just turn all interrupts on or off. So that's what we see in the settings and the status. And for us, a lot of no-op bits. And let's have a look at the status to see why that is. M-status. So this one here is the 32-bit version. So the top bit, bit 31, is SD, and you'll find reference to what all these things mean. But anything that begins with S in this, for the most part, is not of relevance to us, for the most part, because it's to do with a supervisor level, a supervisor privilege level that we're not even going to implement. So I'm seeing we have here TSR, bit 22, and I don't remember off the top of my head what TSR is. Try to find that out. Let's actually just search for it. The trap SRET bit supports intercepting the supervisor exception, so we don't need that. It's to do with the supervisor part. And so I'm guessing that all of those first parts up to bit 17, they're all to do with the supervisor. This part is just sort of a block of nothing. Then we get to some of the machine mode parts. So we have MPRV. So that's the memory privilege in M status, or modify privilege bit. Modifies the privilege level at which loads and stores execute in all privilege modes. When MPRV is at 0, loads and stores behave as normal using translation. So what we'll find here is that a lot of the stuff in the status register is to do with, and is more designed for the idea of dividing up the processor into privilege levels, preventing certain things from happening at certain privilege levels. And for our purposes, it doesn't matter that much if we can do things in user mode and machine mode. They'll kind of blend together, as much as is useful for us in the implementation right now. So all of these kind of things, they're not really going to make a big difference. The ones that will make a difference here are going to be, so is that MPIE? I think that's to do with the MCORs and the MEPC registers. So let's see here. When a trap is delegated to a less privileged mode X, the XCORs register is written with the trap cores, and the XEPC register is written with the virtual address, or in our case the physical address, of the instruction that took the trap. The XTVAL, and X obviously here stands in for like M in our case. The XTVAL register is written with an exception-specific datum, so a piece of data that is going to signify what went wrong here. And the XPIE field of M status is written with the value of the XIE field at the time of the trap. And the XIE field of the M status is cleared. So basically, these are all... So we've got some indicators there of things, certain events happening in the process. So when a trap is taken, we're writing a bunch of stuff to these different registers in order to make sure that it's known by whatever code comes next. Like it can then read these registers and say, oh, this was the cause, this was the memory address that happened at, this was the piece of data that's associated with that. So for example, in an unaligned access, you can imagine that we've got the memory address that happened at, but we've also can say that the MTVAL register, which is our exception specific datum, that's going to be the memory address that we try to access. And so what we can actually do is to make sure that make sure that we take that address and then figure out the two reads that we need to do in that place. True reads, two writes, whatever it turns out to be. So those parts should be clear, and this isn't going to make a big difference for us today, but it's good to get an eye on it. And we have here like the interrupt enable for user mode, for machine mode, all of these different things. So that's the status register. And you can see we start the status register off at 0. Might need to figure out if we need to set some bits up in there, but that's it for now. So here is the base trap vector address plus mode, single or handler. So mtvec, let's have a look. This is the place in memory that we have to put the vector table, the trap vector table. Let's take a look. Let's see what the spec has to say about it, because it does actually have some specifics there. So the bottom 2 bits specify the mode. So we can be in direct mode, where all exceptions just go to base. So we can just put we could have all exceptions go to one handler. We might want to do that. I don't think I'm going to do it for now. Then we have 1, which is asynchronous interrupts set PC to base +4 times cores. So this is us taking our address, multiplying it by 4, because we don't have these 2 bits down here, but we don't need them because it should be aligned. So the bottom 2 bits should be 0 anyway. So what we do is we encode the address here without those 2 bits. But then that means that it's kind of like shifted down by 2 bits. So multiplying it by 4 shifts it up by 2 bits. And then we add on, we take the base and we do 4 times the cores. So we take our base address, which doesn't include these 2 bits. They're zeros for our part. We could shift it, but yeah, actually in hardware you wouldn't need to do that, and we'll see why when we come to build the hardware. In this, we just multiply 4 by the cores. So we take cores and we can shift that up by 2 bits. Yeah, that's it. That will, if we add those things together, it will tell us the place in the table that we need to jump to. So this is the one that I would like to use for that. And I wrote this code also back in November. And what I think, if I look at this now, what I think is the first time around, I was thinking that I would do this in mode 0, because I set those bottom 2 bits to 0. So let's take a look here. So if I put this number in here, we'll see that we had those bottom 2 bits here as 0, and this is the address that we came up with. So I'm changing this whole thing now. So I actually want the address to be, this, right? Which is just the beginning of program run. That's where I want to put that table. Actually, I might want to put the table, I might want to put it here, like 1 off. But that would actually, let's just say for now, we put it at the very, very beginning of program run. We'll take a look at the memory map in a minute, just to refresh your mind on that. But then we need to say that also that this, that we're using, oh no, it should be 1, not 2. Yeah. So our address here is going to be like, wait, so it's the tricky thing now about doing this in so this would be our address, right, in binary, and we don't have those bits here. So those bottom 2 bits are going to be 1, but I actually want to then, let's leave it like this for now. This is fine. Sorry. I should think about this kind of stuff ahead of time. Tried to do some preparation, or a little bit more preparation than I've done in this case. Okay, so here we encode the place where we jump to, or where we figure out what we're going to do in an exception. That one should be relatively straightforward. Interrupt, enable, and disable. Well, that one's quite straightforward, I think. You'll notice that it's set to 888, and if we go back to the spec, you'll see that the interrupt enable, it's also full of stuff that's related to machine mode, also supervisor mode, also user mode. So basically we're ignoring like supervisor mode stuff here, and that's why it comes out like this, 888. Then we have interrupt pending. Well, that's like a different register where, well, let's actually see what it says about interrupt pending. The MIP register is whenever you see this, by the way, an MX length, X length refers to the length of the architecture, so a 32-bit. So it's a 32-bit read-write register containing information on pending interrupts, while the IE register is corresponding to interrupt enable bits. So we could, for instance, if an interrupt is coming in, we don't have to service it immediately in the processor. Like the processor could be in the middle of doing something, like we don't have multiplication and stuff like that. But if it was in the middle of multiplication, it might be like, it might need a few more clock cycles to just be done with it, and it wouldn't make sense to abandon that work. So what you can do is you can actually like just say, okay, the interrupt, we'll deal with it in a minute, but first we need to finalize what we're doing here first. So that can be a good way. You can also kind of like finish out the pipeline or something before you service the interrupt. But often, if you have an external interrupt or something, or a timer, you kind of want to do it as soon as possible. So you don't want to waste time there. All right, that one should be relatively clear as well. We have the cause. Well, the cause, yeah, I thought I made a comment in here about where we could find information about the cause. Maybe it is... Yeah. Okay, so yes, let's actually just jump to the thing. So cause. Yes, so these are the different causes that can happen. So this is the top bit. The top bit up here describes whether something is or is not an interrupt. So it's either an interrupt or an exception. That's what a trap is in general. A trap is any like kind of event that causes you to context switch the code away from something to handle something else. And those can be interrupt driven, which we kind of think of as being kind of events, and exceptions, which are like stuff happened in your program that was wrong, and because of that we need to go and handle that, like error handlers basically, kind of hardware error handlers. So the first bit is reserved for the interrupt itself, like whether or not this was an interrupt. It basically tells you if you're gonna if you have two tables, right? You could have a dedicated table for interrupts and a dedicated table for exceptions, and you kind of need to do that actually. But in those cases, yeah, that's what that tells you. So then you have the exception code, and the exception code is here. And well, so for example, if there was an interrupt and the exception code was 0, it's a user software interrupt. So a software interrupt performed from user space code. Again, supervisor, we won't have that. This one's reserved. This one is a machine interrupt. So we've got a whole bunch of these kind of things. We have timer interrupts. Those are useful ones. We have some more reserved stuff. And everything above 16 is like platform specific. So it's stuff that we could choose to put in there. But basically, yeah, I'm kind of like, I'm probably going to like just do these first 11. Like just have these first 11 in there. And, you know, anything that was reserved shouldn't happen. So there's that. Okay, and then from here, if it's an exception, the first one is like the instruction address was misaligned. So somehow we ended up loading the program counter with an unaligned address. And if that happens, there's a specific address, because that's a special exception handler. And that's different, of course, to when you just do a memory access that's unaligned, because in a memory access, like, you can fix that problem. If you're trying to fetch unaligned instructions, something's probably gone really wrong. Like you wouldn't even know what was happening anymore if you looked at the code in a disassembler, because all of a sudden you're taking like 32 bits that would be, you know, like some instruction, and you're kind of shifting it over and taking the beginning 16 bits of some other instruction, and you're saying, well, that's my instruction. And that really shouldn't happen. That is something that did happen on some old processors, like on some old like kind of microprocessors. It's kind of nuts. Like, programmers did all kinds of crazy stuff back then because of limitations, but in the modern world, you shouldn't have unaligned instruction loads. So that's why that's there. We have a whole bunch of these kind of things that can go wrong. Instruction access fault. I actually don't know what that means in particular, so I would have to do some looking up there. Illegal instruction. You just try to use an instruction that either isn't part of, like, we don't have that extension, so we don't have that instruction, or it just doesn't exist, that instruction. In that case, we would go to here. Breakpoint, that's for debugging purposes, of course. You can basically run some code when the user says, hey, hot, like breakpoint, you know. Load address misaligned, load access fault. We have store address misaligned, store access fault. So these are, you know, when we try to, when we do a load or a store and they didn't work. Environment call, instruction page fault. Anything that's to do with page fault is not useful for us because that's like a virtual memory concept. We're not going to have virtual memory. So yeah, so we have all of these things. So basically we just need to make a table of all of these and fill them with the right instructions. And one of the things we'll do just after this, we'll go and look at the C code, how we actually define this table and how we define the handlers, the kind of how we would write code that says this is the handler that deals with this thing and now it's in the table. All right, I think we covered almost everything now. So that was the cause. The next is the exception program counter. That's where we just place the instruction address that we were at when we change context so that we have somewhere to go back to. Yeah, it's our storage space. We have a general scratch mode register that we can use for contextual information. We need to see how that gets used. Probably we'll need that, for example, when we're doing unaligned access. And a trap value register can hold the address of a faulting instruction. It can also do a whole bunch of other things. So we can just hold a value there that's specific to the trap. All right, then there's actually one more. And it's not a CSR that's in the CSR space, but it is a CSR. And that is the time compare register. And this is a really cool one. This is a really useful one. It's another 64-bit register, but this register we actually have to expose it. We have to expose this in a memory mapped way. So the only way the user can get to it is by reading and writing a memory address. And what we do here is we can put a timestamp, like a tick count. So something that's in the same scale as our timers, right? So when I say our timers, I mean the things that we wrote before, like the cycles. We can write a value in here, and then when the timer, the machine mode timer in this case, but you know they'll all just be the same cycles. It's all just going to be coming from this one register here. When this number equals whatever is in the cycle count, then that will cause an exception to take place. The reason that this is super awesome is it allows us to do actual like timing driven code, and that's a really that's the basis of any useful thing we'll do with this. Like if we want to if we wanted to have this thing without building special hardware for it, if we wanted to have our processor do PWM generation, like generate square waves where the width of the square is, well, it's not a square, it's a rectangle, right? But the width of the square wave is defined by, you know, something. If you want to drive motors or control brightness of LEDs or any of those kind of things, you use PWM. This would allow us to actually do that because we can actually do something at the right time. So that's how we would use that. That is all the registers. So here they're exposed with their addresses. And apparently I'm not using this, I'm not properly using this thing here yet because I'm doing mWrite, but I'm not doing it mRead. So here I should use the enums for all of these things, but I haven't done that yet. In any case, we can read and we can write these things. And some of them we can only read and write certain parts, so they're masked off. This is also written in the specification, like what bits you're allowed to write. what bits like will be ignored, which bits you're not allowed to write. So all of that stuff is in the spec document. I'm going to keep this implementation probably pretty relaxed about what you can and can't write to these CSRs. Like, I'm not going to freak out if you write to something that it says that you can't, especially if we don't use that thing. All right, so now as far as I know, we've looked at these things, right? We've looked at the CPU capabilities, manufacturer, version, various registers that hold data for when interrupts or exceptions are taken, and some memory mapped registers for timers, right? We've covered that stuff. Let's now kind of go and look at some of the C code and some of the things that I talked about before of what I've done in the last couple of days, and see how this kind of translates, because, before I got really into this kind of stuff, the idea about, like, even if you have some experience writing C, like on a x86 processor or something, or other low-level languages, right? You write a program, and typically you start in the main function, and that's it, right? You write C code, you do a bunch of stuff, and then it creates an executable program at the end for you. And that executable program, depending on whether you're on Windows or on Linux, that's going to be like that's going to be in some sort of container format, like an ELF file or a portable executable if you're on Windows. And that has more than just the code that you put inside it, right? That is filled with information, like, and also there's like, you'll notice if you run a program that you wrote in C, it doesn't begin at the main function, right? It doesn't start there. There's a whole bunch of other code that runs first. And so there's this whole bootstrapping that happens behind the scenes. And when you're working with like an established processor or even established microcontrollers and stuff like that, a lot of the time you don't need to worry about it. Like, you just start at main and things will work as normal. But if you're like really building the system from the ground up, or if you're writing an operating system or any of those kind of things, like you need to start going to those levels that go below. And that is when that's when we start to see that kind of stuff. So this is like the super simple code that runs in the beginning of a program running here. And I've talked about this in previous episodes, but this is some assembly. We've looked at a lot of assembly of RISC-V here, so this shouldn't come as a surprise. Basically, we're defining a symbol called start. Like, the start symbol is kind of like the compiler understands that this symbol, this memory, like this is where code begins. We're going to end up putting that somewhere in memory, but this is like the thing that should execute first. So what we do is we set up the stack pointer. Then we call this function that loads the initialized global variables into memory. I talked about that earlier, right, with the C program. Like, this is how, like, when we're down here and we talk about other global, that we can actually, refer to this 42 value. We do this copy initialize vars, and that is defined in this other file, which is a C file. So this is already quite nice, right? You can mix and match assembly and C in this kind of boot up process and write this in whatever thing is the easiest way. Here you can see we're taking in some external variables. We're saying we have these variables, they're coming from somewhere, but we don't know where yet. And these are things like program end, the start of data, and the end of data. And these are all symbols given by the linker, which takes all of our code and kind of figures out like how to compile that so that it's all relative to the memory map that we have defined. The memory map, just as a little reminder, like program ROM begins at this memory address, 10000000. Program RAM begins at 20000000. So that's kind of like, we've got different places in the address space. Some of it's completely empty, like everything from 0 up until this, which is quite a lot of memory, is just unused, right? Obviously, we don't have all of this memory in the tiny processor we're going to build. But we have the whole address space. So we can use the space of the address to map in certain parts. So this is where program ROM is mapped. This is the code. If you write C code, you compile it, you put it in. It's going to be in the ROM space or flash space or whatever we're going to think of it as being. And then there's going to be a RAM space. So that's just like, where you put your variables and the stack and everything that's dynamic, right? Everything that needs to change at runtime, that needs to go in RAM. And so our program needs to understand, for instance, that if we make a variable, like this variable needs to go into RAM. Even though the code needs to go into ROM, like we need to write this whole thing so that all of the memory addresses are relative to these address regions that we define. Okay, so what this little piece of code actually does is it grabs some of these these variables that define some of this stuff, like where our code is going and how much space it takes, and it's actually copying like the initialized variables. So there's some place in memory that's going to hold that value 42, and that's going to be in ROM because we load it with our program, because our program knows this should be 42 in the beginning, but it needs to load that into the RAM location that actually the variable thinks is associated. Well, the variable is associated with that memory location. So this other global has a location in RAM, and we need to copy this value in. So this is what this little piece of code is doing. It's basically a function called memcopy. That's all it's doing. It's just taking one location in memory and saying, take what's here and put it over here in this one. Won't go too much into it for now. So that was that's the memory map and the boot code. Oh, the last thing that we do in the boot code, of course, is like after we've done that, we just jump into the main program. And there's probably quite some stuff missing from this. And right now this is called the bootloader, but it's not doing what a bootloader actually needs to do. And we'll talk about that in future when we actually have this whole system up and running, like what a bootloader really will do and like kind of why that's useful for us. But basically what we really want is to be able to have like this little bit of code, or we want to have just a small piece of code built into the CPU somehow or some region of memory that will load other more dynamic bits of code that we can bring in on the fly. But right now we don't have it, but this is kind of fulfilling our basic thing that we need to do, bootstrapping the whole flow. All right, so then we have the interrupts. So let's think about this in terms of the memory map. Here we have program ROM from this address until this address. So we don't actually have that much ROM, but we're going to use a technique called mirroring, so that like if you read the very last ROM address and you go to the next one, you end up sort of wrapping back around and reading the first one again. So it's kind of mirrored a bunch of times over and over again. So what I'm going to say is that at the very beginning of this thing, that's our exception table. So that's where we put exceptions. These two could be swapped in the spec document. The interrupts come first, and then the exceptions come afterwards. It doesn't really matter. There's no like, this is going to be like something that we define. It's not specific to RISC-V. However you implement this, it doesn't matter as long as your tool chain supports it correctly. And we'll talk about kind of like how all of this works, like how we define our own kind of like rules about how programs need to be on our system, and what that kind of means for like kind of other users. Like right now, I'm the user of this thing, and I'm both the person building it and the person using it. But in the normal world, of course, if you build a chip, you sell it to people and then they use it. And so they're your users. They want to be able to have tools that make it easy for them to not worry about any of this stuff, right, that we're talking about now. So you kind of need to figure out a way of building libraries and tools and stuff for them to be able to do this stuff automatically. I haven't figured all that stuff out yet, But in any case, this is kind of going to be the layout. We'll have the exception table, then we'll have the interrupt table, and I might have the numbers here wrong because in this calculation, I think I actually skipped those reserved addresses, but I think it will be easiest to actually include them because that will make the calculation of our, like where we jump to, a little bit easier. And I don't really want to venture too far away from what the spec says here, like with regards to those numbers. Then we'll have the end of that table somewhere. So we'll want to have a symbol inside our program that says this is the end of the table, just like we saw in the code just now. We've got these symbols and we can get them and figure out, oh, this is a memory location, this is a memory location, that kind of stuff. We kind of want to have one of those that says this is the end of the table and thus is the beginning of the actual program. Okay, so then we've got a header file here, and this header file it defines a couple of things. The main thing it does is it basically defines a whole bunch of names for the vectors. So you'll see here we've got the vector interrupt 0, which is a user software interrupt, vector interrupt 1, which is a supervisor software interrupt. So it's basically a copy of this table. Actually, it's not quite because it misses the reserved entries, which again I want to put in there. But for the most part, this is now sort of the two tables. One for exceptions and one for software interrupts. Okay, so all this does is say that this name that can be used that has, that actually describes what this does, this can be used as a library, so to speak. That maps to this well-known name, vector underscore interrupt 0. Like that's going to be what the program thinks of as being the name of this thing, and then this is what you can refer to it as. It's kind of a mapping. And then we have some let's actually take a look at this, right? So the way in which we would define like the code that runs for an interrupt is kind of like this. If we wanted to make an interrupt for when the user did a software interrupt, let's say, we need to write a function. So it's a function that doesn't return anything, and let's just say it has this name. This is the name of it, and let's say it doesn't take any arguments, and this is it. This is the function, let's say. And then we do return. So this function doesn't do anything, but like how do we tell the compiler like this is a special function? How do we tell it like where to put this function? Because it's, well, we don't really need to tell it where to put the function, but how do we tell it generate special code? Because there's going to be like, actually I don't think we necessarily need. I'm trying to remember if there's a specific return from interrupt instruction, and I can't remember if there is, but let's say there is for the sake of argument. We need the compiler to know that it shouldn't generate a regular return instruction, it should generate a return from interrupt instruction. So the way in which we do that is we can use attributes, and these attributes are from the compiler. So what we would do here is we kind of add an attribute label here. And this is just it doesn't do anything in the code, but it's a message to the compiler that we want to do certain things. And you can put quite a lot of things in here. It's documented on the internet. If you search GCC attributes like this, you'll find all the different things you can put in. And that's like everything you can do in C code in general. And then for different platforms, they'll have different specific things you can do. So one of the things we can do is say, hey, this is an interrupt. Generate interrupt style code here. So generate a little bit of code in the beginning that sets the interrupt up, generate a bit of code at the end that kind of tears everything down. And, if we were to have a special instruction for return, make sure that you use that one instead. So that's what that little piece of kind of magic magic dust does for the compiler there. So this is how we would do that, right? And then if we wanted to then put that in our vector table, you can see here I've got something that says vector table, and then it kind of has a big list of stuff that corresponds to those two tables that I described. Well, what we would do here in that case is we'd say, actually, this one is not the default interrupt routine that I have here defined. It's actually this one. And so this just says the address of, so this says the address of this thing. So we're just putting that one as the first value in our table. And so that's how we can do this in this case. I kind of want to streamline this whole process so that the user never has to deal with this part, but I'm not quite sure of the best way to do that yet. But I'm also not worried about it yet. So this is how we'd write it. But this is a bit hairy for a user to write. So what we can do is we can use something called a macro. So what a macro allows us to do is to say the user writes this, ISR with ISR type, so that's going to be one of these, and that then generates this piece of code that says void attribute interrupt, and then puts the name that we gave here as the argument. And so instead of writing this, we'd actually write, I've already forgotten, it's just ISR. We would do something like this. And we would then define our interrupt service routines like this. So ISR, the user software interrupt, and then we put our code in here. And that's a nice thing. I mean, macros, there are many cons to macros as well, but for this kind of thing, it can make life a little bit easier, kind of defining a simpler approach, a unified approach for you users to do stuff like this. So that's the reason I'm doing that. And also, macros work very nicely in this case where we don't want the user to actually write this, which is basically what this would be. So actually this is how we would end up doing that. And what you might then wonder is, well, one, like, what does this vector table mean? Well, you may have seen it here. It's also a macro, and it expands to this. So let's comment that line out and replace it with what it actually is, which would be this. And the ISR name there is going to be this. So what we're saying is this is a static, constant ISR function. And an ISR function, this is basically just saying it's a type of a function that takes no arguments in and returns nothing. That's what this is. It's like C doesn't have the best syntax for defining this, but this is the return type. This is the name of the type for some reason. This just says that it's a function, this part. It's like describing a function, and this is the arguments. So it's not the best syntax in the world, but that's what we're stuck with in C. So we have a static, constant ISR function array that's called vector table, and then we use another bit of GCC magic here to say that this needs to go into a special place, or it needs to be put into a special section inside the ELF file, the kind of the file that gets generated from the compiler that is more than just your code. That's a whole bunch of information about organization and stuff, and maybe debugging information and all of that kind of stuff. We want to put that into a special section that we're calling vector table. So that is what this nice piece of code, this nice little macro expands to. So let's take that and put it back here. So basically, that's what that is. And also, I've just realized that this could also just be like this, right? This could also just be ISR, and we just call it default ISR. Something like that. All right, so this is what this whole section is. And right now, the whole table is just filled up with this one function that does nothing. So every single one of these, like if we had any exception occur, like no matter what value we calculate here, we're going to find the address of this function, and that's what we're going to run. And this function is going to contain a little bit of code, but it's not going to do basically anything. It's got nothing going on, so you can imagine that it does basically nothing. After we understand all of that, the question that comes to your mind is like, may come to your mind, might be something like, how does this table appear in the right place? Like, how do we put this into where we say it should be in the memory map? Because we're saying, hey, these things should go here and this part should go here. How do we make that happen? Well, right now, by the way, it's not in that order. I have these in the wrong order, so I'm just going to say that the interrupt table comes first, because that is, well, it's equally fine. So the interrupt table comes first, the exception table comes after, and it goes at this address. How do we tell the system to do that? That is what we use the linker script for. And this is a whole extra language that is there in the world. It's not the easiest thing to figure out in the world, and it's not something that you're faced with very much. But occasionally you might need to bump into this. And the linker script is like used by the compiler. It's a function. It's a functionality that's built into the compiler. It has a default linker script that it runs. So basically, if you don't provide one, the compiler will go, oh, I'll use this one that I have over here. This is how I link programs together. And the idea here is that with languages like C, C++, Rust, Go, Zig, like low-level languages, you build stuff in units, right? You don't build like the entire program all at once, because you can have huge programs. What you actually do is compile little bits and pieces of code over time, and then you have to link all that stuff together. And the linker script is basically the thing that says how to link that stuff together. So in this case, it's RISC-V. We have an entry point that's called start. That's this thing. That's this global function. This is what tells us to expose this as a symbol. And yeah, then that goes into the linker script, and that says that's where we start. That's the code. We can use provide to provide a bunch of information around to the program and expose variables into C code and assembly code. But the main things that we do here is we define the memory map. And notice here the memory map is basically what we have in that file. It's like, here's program ROM. It's readable and executable. It's not writable. And it starts at this address and it has this length. And this is just what I'm saying it has right now, right? That's like an arbitrary number that we're using for the emulator. But when we come for the real hardware, these things are going to change. Then here we have RAM. It begins at this address. It's readable, writable, and executable. So we can load programs into RAM and we can jump into them. We can actually execute them, which is, in many architectures, is not something that you want to allow. Sort of your data areas and your data and your code to kind of coexist in the same space, but that's not something we're going to worry about here. So we define this memory map, and then we define kind of the sections, and this says how to put the program together. So in this ISR, where we talked here about sections, right, this attribute, we're saying put this thing into the vector table section. Now, by default, code will go into something called the text section. This is just, if this is all really confusing, now don't worry. It's like, I know these are a bit like tricky concepts, but like they're actually quite simple if you boil them down. There's a lot of kind of legacy and stuff going on here, but in essence, code goes by default into a certain section. We can tell it to go somewhere else just by using this attribute section thing, but by default it goes into the text section. And what we're doing here is we're saying, hey, we've got the text section. This is how we're going to deal with that when we come to build it together. So what we're doing here is we're kind of like putting the program together. So what we do is we take the text section again, and here we're going to start also referencing other sections and putting them together. So what we want to do is we want to say, actually all the vector table stuff, that's going to be right in the beginning. So whatever you've got with text, first we have the vector table. And here we're just defining two variables either side of it that says this is the start of the vector table, this is the end of the vector table. So between those two variables, which we can get access to in C and assembly and stuff, now we know the size of the table, we know the addresses of it and everything. We should know those anyway, we could calculate them. But if we change things around, we've got these numbers, we can use them dynamically. Here we're saying keep the intersection. I'm not exactly sure what the keep really means here, but we're doing it anyway. I copied the base of this file from someone else. I'm not a linker script expert by any means, but this is kind of what I've gathered from figuring stuff out. Here we have just all the code. So if the code hasn't been given a special section, the code just comes immediately after all of the vector table stuff. Then we can also take the read-only data. So this is data that's marked as const. So if you have some variable that you want to use in your program, you can make it const, right? And you can say this is never going to change. And in C's world, in the world of C, you actually can get rid of const. But if we put something into ROM and you can't overwrite it, that thing will be const. So we can just put those variables inside the program ROM. So if you mark something as const, it's really const. There's no way you're going to change it in this case. So that just ends up going into the read-only data. So that's what happens, and then we have the program end. These are all just variables, right? So the end of the read-only data, the end of the program, they're the same address. All of that stuff ends up going into something called the text region, and the text region is just the program ROM. It just maps to this name. So we're just saying it goes here, and we're this program is keeping track of the address of where we are right now, and it's going to, if we try and jam something else into the region text or the program ROM, it's going to start after everything that we've just said. If you've seen my 16-bit VM series, you'll know that we built an assembler in that, right? And the assembler had its own process for doing this. It didn't use linker script, but it uses something similar to describe the process of where the code goes and how to kind of put the code together, which is essentially doing the same kind of thing, only it's integrated into the assembly language itself. So that's kind of the difference there. But there's quite a lot of benefit to doing it this way, but it also adds complexity. So in the 16-bit VM series, I wanted to avoid all this legacy. But it's basically doing the same thing. So if you understood what was going on there, you basically also understand what's going on here. Then we have data. So data is all the variables, right? That's all the, for example, in the main program that we saw here, we create this other global that's somewhere in RAM, and it's just a variable, right? It's something that exists. So that goes into the data section, and that's what we're doing here. So don't worry too much about this whole global pointer thing. We'll get into that some point in the future. Basically what we're saying is, okay, take anything that is called sdata, sdata2, or data, depending on various bits of legacy and different compilers and whatever. That data might actually end up in different places, different labels. I know for a fact that mine ends up in a section called data, so I don't really need this stuff, but it's here just because I based this on someone else's code, which is at the top of this file. And all this code's on GitHub, so if you want to check this out in detail, if you want to look at what this is based on Ferris, who's also in the past, I'm not sure if he's still working on it, but in the past made basically everything that we're doing, but on a whole nother level. So he was also making a RISC-V processor on an FPGA, using his own language built in Rust, running Rust code. He also built a graphics processor on it. Like, he went crazy and did a whole bunch of stuff. I based this on something that he had here, and this is probably way more advanced. But this is where that comes from, and you can go and check out all that stuff if you would like to. You will notice also there's a whole bunch of like align for and that kind of stuff, and this is just about making sure that the data actually ends up on the right boundaries, right? That we don't end up crossing over data boundaries, because we don't want to do that, especially for the code. So the code up here actually explicitly said for this whole thing, it's aligned on 4-byte boundaries. Like, everything you put in this should be 4-byte aligned. Don't randomly put something on byte 5 and then start from there. It will be the same for the data. The whole thing should also be 4-byte aligned, I think. I'm not actually sure about that, but in any case, I don't do it in the beginning, because I think that if you have smaller bits of data in the RAM section, it can be okay, right? Because we always need to fetch 4 bytes, but like we don't need to use 4 bytes for everything. And then we have the BSS section. I'm not sure what BSS stands for, but it's basically it's a kind of a virtual section that allows you to understand like how much data you had in total. Like, actually, I don't use any of this stuff on the BSS. You'll notice that when we are copying in these variables, we're using this sData and eData labels, and those are these labels, right? The start of the data is up here, and this is the end of the data. And so this whole thing is not used, so I'm not really even going to go into this, but the BSS is kind of the idea of the uninitialized variables section, right? So like this would be, the start of that and the end of that. I did actually try and use this. There was something going on where it seemed to be like 4 bytes too short, and therefore it wouldn't copy all the RAM. I use this, it ends up being really reliable, and we put this in the region data, and the region data up here maps into the RAM. So we're saying that this stuff, like, we're assigning symbolic values that begin at this address. So if we have, for instance, in the main program, this variable, since this variable ends up in data, and the linker goes and looks at the data section and puts that somewhere, this variable is going to end up like probably at this specific address, right? Because it's going to be the first thing that's related to that. So that's what's going on there. That's it. That's the linker. I hope that actually makes some sense, because this is confusing to me. It's still kind of confusing to me now, actually. I think you can go quite in depth with the linker and really making it generate stuff effectively for you. So right now, if I go into this system code directory, there is a make file, and the make file is basically contains all the commands to actually build all the C files and get the program out. If I run make now, that runs a whole bunch of commands. So first it runs this command. Actually, let me do first make clean, so it removes everything, and then run make. So it runs a whole bunch of like make this directory if it doesn't exist, but we can ignore those. So the first thing it does is it runs the compiler, and it runs it on all the different C files and the assembly files. So it runs boot C, and we get out of that a boot object. So that's only the stuff that's defined in that boot object. Like, it's not referencing any other C file. So even if we refer to things that come from outside that file, at this point, like, that doesn't know about them. It only knows that something might exist. So in the boot file, the boot.c, we actually know that we refer to things that come from outside. Like, these aren't defined inside, like, they're external. So we can compile just this piece, even knowing that there's something that should come in that isn't there yet. But we can still just compile that piece and say, you know, if nothing changes, we don't need to compile that again. That part's good. So then we've also got the ISR. We do exactly the same thing. So we get out an output file for that. Same for the main.c, and same for the bootloader. And then when we have all of those pieces, we run the compiler again, but this time we run it slightly differently. We run it with the linker script, and we pass it some additional flags about like how all of the kind of surrounding code should be linked together. And then we pass all of those output objects, the object files, we pass all of those and we say build that into one big kind of complete linked file called main.elf. And the elf file contains now all of those sections that we just talked about. It contains the program ROM text section. It contains the data section. And it's got all of those symbols and worked out where they need to be and how big things are. And it's basically took the pieces of code here that were defined in boot.o and with these symbols, and now it has references to these symbols because they come from the linker script. So it's linked everything together for us. And that goes into one big file where all the data is present. The problem is that, and I've talked about this in previous episodes, so if you're just thinking, oh, this is, you know, repetition, please bear with me. I just want to make sure all this stuff is clear before we move forward, because we, like, in the future, we're going to be going quite deep into a lot of these concepts. And probably not going back over them too much. So I just want to make sure they're crystal clear at this point. Once we've built the elf file, which contains all that stuff, what we need to do is we need to get just the data we need out to give to the emulator and eventually the FPGA. We're not going to load the whole elf file in because the elf file contains tons and tons of information. What we want to do is build the core, like just the code, just the vector table, just the initialized variables. We want to pack just that information and give that to the CPU, and then that's going to be what it runs. So we need to run a couple more programs after that. We run object copy, which is just a program that can extract bits and pieces and copy data out of elf files. Probably other files too, I'm not sure. This one is getting binary data out from the text section of main.elf and putting that into a file called main.code. And then it's doing the same thing again, but with the data section and putting that into main.data. And then what we're doing is just joining those two files together. And the beauty here is that the way we've written the code is that it knows like where the program ends, for example. So what it does is it says, like, this data is going to get loaded into the like the memory space of the program. It's all going to be in ROM, right? This data that comes out main.bin goes into ROM. And so what happens here is we say, hey, this is where we're starting in ROM at the program end. And here's where the RAM data starts. Here's where like our global variables begin in memory, as defined by the linker script. And what we want to do is copy what's in RAM at the end of the program, so the beginning of the data, right? Because we just say first the code comes, then the data, and then they're just like together in one file. And we're just saying, copy the data part that's in ROM, copy it into RAM, and just like move through all of that. So that's how our data gets in. So that's the whole flow right now of how we go from stuff in the compiler and defining files in C and assembly, mostly in C at this point, also assembly, how we get it into our how we get that into the processor itself, and how it's kind of bootstrapped to the point where it can actually run that code. So that is the whole step. And the reason I wanted to show all of that is because I think it's really important to understand, like, that we don't just have this abstract thing called a vector table that's defined by the RISC-V specification or something, right? It is barely defined there. They don't say how we have to do that. So we have to figure out a way that makes sense. And incidentally, you know, I haven't invented this from nothing. Like, this is basically how this works in every microcontroller, at least. And also processors, you know, processors have, when I talk about processors, I'm talking about like x86 and x86-64, and the ARM processor and that kind of stuff. They're doing a similar kind of thing, right? But there's more layers because of privilege levels and because of memory virtualization and that kind of stuff. But in the case of like a microcontroller that doesn't do any mapped memory, like virtualized memory, this is pretty much the procedure that is going to take place. So I think it's really important to understand that it's not magic. This is how it works. And we can write the C code, we can write the assembly code, and there is the part that really makes things come together is this linker script. And so at every single point of this whole process, we're in control of like what code gets generated, what data gets generated, where it goes, how it's generated, like what messages we can tell to the compiler to say, hey, this is like this kind of piece of code, so generated this way. And now I think is a good time to actually maybe take a little look at, let's close this window down for a second, and let's take a little look at what that ELF file looks like, at least what some of it looks like. So I'm going to run RISC-V, wait, how is this? RISC-V 32, yeah. So I'm running a program called object dump, which just dumps out stuff from the ELF file and disassembles it. And I'm telling it to tell me everything that's in the text section and everything that is like all of our functions, and also the data. It will show us the data as well. So, and it's going to show us the memory addresses that it references, right? Because the linker script knows about all the memory addresses. So it's a really good way of, without even running any code, to know what's going on here. So this looks like a whole bunch of add instructions, but it's actually not. This is the vector table. So what we'll see here is that this is a memory address, right? Split across what it thinks is two instructions. It's kind of interesting to me that oh yeah, so okay, this is like the opcode, and then we have like, you know, the specifics here, but this isn't accurate. This is an address that is 100000B8. So if we go and look at that memory address, 100000B8, so that's going to be down here. That is the default ISR. So if we go back here, that's this function, right? And that is what every entry in this table is pointing to. So that's what's going on there. And notice that it's not completely empty, this thing. We've got some setup, like I mentioned. We've got some teardown. We've got a no-op in the middle for reasons, why not? And we have an M return, so that is the specialized return, right? This is I guess we're going to need to implement this instruction. But yeah, this is an instruction that basically says return from the interrupt, return from this machine mode handled interrupt vector. So that's that. So this whole table is just a series of these addresses, right? Maybe we could even change one just to see that there's a difference in here. But that's what that table is. And then immediately after that, we see that there is this copy initialized vars copy initialized vars piece of code. And then we have that default ISR. Then we have main, right? So that's actually the main function of the program defined in main. Then we have start, which is defining everything we have here in this part. So we've got all of the code, but the tricky thing that we have right now is that, then we have the bootloader jump, which is the last thing. And then we can see also the data section down here. And you'll notice that what it's saying is that there's other global at the very first RAM address, which is 2A. And if you know your, Hitchhiker's Guide to the Galaxy well enough, you'll know that 2A is 42. So that is what we assigned in main.c. So that's the data that we defined. But the interesting thing is that this data is also in the ROM. We just don't see it here because it's like the program ROM hasn't been made yet. Like the thing that we load into the code, we do that by dumping out the different sections into we dump the different sections out into like binary files. So we'll see them here, right? We have main.code, main.data. And if we take a look at main.code, it's not there. It's actually in something called build main.code. So in build.main.code, you'll see that we have the vector table up here in the beginning. So this first bunch of data is just the vector table 100000b8. This is little endian, so we have to read the bytes, from right to left, basically. And then we have all the code here, and then after that we have the data section. The data section just contains 2A, right? A 32-bit value, which is 2A, which is 42. And when we concatenate those two things together, we have the vector table, we have all the data, all the code, and eventually at the end we have the data after everything else is complete at the end. So this is what we end up feeding into the processor, just this small file. So if we compare the output of the build directory, we'll see that the main.elf is 9 kilobytes, whereas the main.bin, which is like this part, is just 276 bytes. So it's a big difference. That's why we don't just feed the elf file into the processor, because 9 kilobytes on a microprocessor is quite a lot. So this has been a bit of a tour through kind of where we're going on this reinvigorated journey on the RISC-V series. Of course, I wanted to get to more, so I wanted to do this part, which was start implementing and testing a trap. But I think I'm going to leave it here because this video is already getting long, and I'm going to try to get the next video in this series out quite quickly as well, where we really will dive in. But this is, as far as I'm concerned, this is a really good. It's been a kind of a theoretical part, but I think this is a really good foundation to move forward and get kind of running on the project again. And so if we just think about where we're going to go from here, it's going to involve going into, in the case of, let's say, the unaligned access. Well, we're going to take an instruction. So we're going to fetch an instruction. So we're in here in the instruction fetch stage, and then we're going to move into the decode stage. And at some moment, we're going to know that this is a load. We're going to know it's a load or a store, right? Or something that looks into memory. So we're going to be in this piece of code here. And remember again, this is hardware. So like everything that's happening in this piece of code is really just assigning a bunch of values into a register. Kind of computing values by doing Boolean logic operations like and doing shifts and doing comparisons and that kind of thing. Those are all just like digital logic operations that will literally turn into hardware. What we can also do is check at this point if we had, well, we don't even need to check if we had a load and it was unaligned. We could actually just calculate if like whatever address that we end up calculating is unaligned. And we'll pass that on to the next stage, which is maybe execute. And at this point, we can actually check like, one, are we doing a load or a store, and is it unaligned? And if it is, at that moment, we can actually kind of stop the processor, like signal to the processor basically that it should store. We have these functions in here called should store, and at the moment they all just return true or false depending on whether this is the current stage of execution. But what we need to do in this case, whenever we get to an exception, in the place where we recognize the exception, maybe not, I need to do some research into how best to design this from an actual computer architecture perspective. And if you have resources on that kind of stuff, then please feel free to share them in the comments as well, because I'm going to look myself at some different things, but if you've found something in your own journey, please share. I might want to design a module or something like that whose job it is to basically handle when something goes wrong. And probably what it will be is that like for one clock cycle, we'll go into a mode where we figure out kind of how to set all of those different CSRs and everything to the right value. And then on the next clock cycle, we'll kind of we'll go back to the beginning of execution and we'll like start executing the from the exception. So we'll kind of like flush out the pipeline at that point. And and in the future as well, when we're doing parallel pipeline, this is going to be something that we need to think about a bit deeper as well, because we're going to have potentially 5 instructions running at a time, but only one of them is going to be causing the fault basically. So what we kind of want to do is pause that one, let the rest of the instructions execute, and then kind of do the recovery, so to speak, the trap. So what that's going to involve is like, basically putting some data in here that throws up a flag and make sure that the data is available to that module that's going to handle exceptions. Make sure the data that it needs is available to it, and just pause execution, let it take over. That's what I think the design is. And if that hasn't made any sense right now, then don't worry, I don't have it 100% crystal clear. I'll draw some diagrams in the meantime and figure out something that seems to make sense. For now, I think that's probably enough. I want to thank you for bearing with me, for sitting through such a theoretical episode. If you made it to this point, you're awesome, and you're probably really happy that the RISC-V series is back. You're probably one of the people who was asking, like, where's the RISC-V series? So, I hope that you're psyched up for the next part of the implementation, because I'm actually really excited to get going on that next part as well. Thanks for bearing with me up until now. If you're also a patron, or you're thinking about becoming a patron, well, one, thanks to all the patrons who are patrons, like patronize. That's not the verb, but for the patrons of this channel, a big thank you. I don't say it enough. It's a little bit because I'm not embarrassed by the whole thing, but I feel kind of it's the part that, like, I like to just share this stuff online with everyone, and the Patreon is there because it allows a lot of useful stuff, like buying the equipment that was much needed for this channel to progress and all of that kind of stuff. But it also affords me like the ability to get resources and to buy hardware like the FPGA board and to do all of those kind of things. And it basically gives me the license to do those things and pick projects up like that, knowing that I can use them on the channel, and knowing that there are people who are on the other side who are going to think that it's a worthy use of time and money, right? All the money that I get from the channel, I just use on the channel, right? I don't use it on my everyday life. So that's that. Thank you to all the patrons. I haven't planned this out, so it's yeah. Apologies for it being about as unprepared as the rest of this video. If you do want to become one of those people, you can go to the Low Level JavaScript Patreon. It's linked below. It's also just patreon.com/lowleveljavascript. And it really helps. It's also just a nice indicator of like, oh, these people joined because they like RISC-V. You know, these people joined because they like the hardware reverse engineering. These people joined because whatever the video may be. So it's also a good feedback mechanism for that. That is it for now. I'm gonna not make it so long between this video and the next video because I want to get to the action, and I'm sure you do at this point. But this is the end of this one. So have a great day, week, month, whatever it is for you now. And I'll see you